Welcome, welcome. Last episode, we were looking all about the conventions of understanding cells and batteries. Now we're actually going to look at the chemistry that's going on within there, and not just convention how we look at it. So, without further ado, the chemical reactions within the cell. So remember back to our zinc copper Danielle cell. We say is going on as the zinc dissolves and copper is deposited. What is actually occurring? So left cell, zinc is oxidized. Following reaction, zinc solid goes to zinc 2 plus and 2 electrons. Due to the convention, this oxidation cell is called the anode. The right cell, the copper is being reduced. 2 plus 2 electrons goes to copper solid and it's called the cathode. The overall reaction is zinc solid plus copper 2 plus goes to zinc 2 plus and copper solid. All reactions can be generalized as anode. Reduction 1 goes to oxidant 1 plus V coefficient 1 electrons. Cathode is oxidant 2 plus V coefficient 2 of the electrons plus reductant 2. And gets to the point where we have to cross multiply by the coefficients. We have V2, nu 2, reductant 1, nu 1, reductant oxidant 2 goes to nu 2, oxidant 1, and nu 1, reductant 2. So this essentially takes into account the greatest common factor between the two electrons. If this is 1 and this is 1, all this is 1. This is 2 and this is 2. Well, you could simplify this in the end. We're 2, 2, and 2 and 2. But it's just taking into account how would we balance two half reactions together. So how does this cell potential relate to our Gibbs? Remember, Gibbs is the sum of our chemical potentials. Well, we said we're looking at the electrochemical potential. So electrochemical potential of zinc ion, ECP of copper minus ECP of copper 2 plus and ECP of zinc solid. And we said, oh, the metals were 0. So we can simply say, well, then it's chemical potential of zinc, ECP of zinc ions, standard state, minus ECP of copper ions on standard state, plus RT, ln activity of these two, products over reactants. And if this is at standard state, we can just absorb that into Gibbs. So the Gibbs non-standard equals Gibbs standard plus RT ln activity, or essentially our K, or RQ really. So remember that electrochemical potential of a pure neutral element in the standard state is 0 at standard conditions, so that makes things easier. We also said that delta G non-standard is electrical equal to work electrical, which can be calculated by negative moles times Faraday's constant times the change in chemical potential, change of electrical potential. And this can be measured by the potential differences generated by the particular values of activity of zinc and activity of copper. And N is the moles of electrons. So for a reversible reaction, we'll replace the delta phi with E, or electromotive force. So that is where we give delta G equals negative NFE. We've seen that. But we can also say delta G is equal to, well, you can say negative NFE is equal to delta G naught plus RT ln activity or reactivity. Now, because at the standard state, activity is 1, and delta G naught equals negative NFE naught, we say that for E equals E naught minus RT NF ln Q. Q is the reaction quotient made up of the activities. And this is essentially our NERNST equation. Essentially, we change it from electrochemical potentials into electrical potential or cell potentials. But this is just a fancy way of looking at something we learned in general chemistry. How do we actually find the E cell? Because delta G standard is equal to negative NFE standard. The nature of the reversibility of electrolytic cell, we can simply say E standard reduction is equal to E, the opposite of E standard oxidation. So any oxidation reaction has an equal and opposite Gibbs energy. So one thing about E cells that it's an intensive property, because delta G, E cell is equal to delta G standard divided by NF. E does not change with the stoichiometric coefficients, because N changes, so does delta G. So delta G is taken into account N. So as those two change, they change identically and cancel each other out. So we can simply say that the cell potential is the reduction potential plus the oxidation potential, those two. But because of this, E is not a state function. So we need to go through Gibbs if we need to do anything state function related. So this is only through a specific term. If we need to change this, take an alternative path, we have to go through delta G first. That is problematic. Got to be careful about that. So how much voltage would a lead acid battery produce at 298 if sulfuric acid has a mean activity, ionic activity of 0.2089 when at 1 molar? So this is actually a lot easier than it looks. So I'm going to go ahead and skip this step and say, like, hey, you're going to have to look up these values. This is something you should know how to do. You look up these values, you find this out. E standard is going to be, well, you look at oxidation minus reduction. So this is all the reduction cell potentials. Lead oxide is 1 as written, so 1.685. That lead sulfate is opposite as written, so that's going to be, so that's going to be, you flip the sign and add them, so add on 0.356. You do that, and so you're going to say 1.65 plus 0.356, flip the sign. The E standard is 2.041. Now, minus RT, so R is 8.314. T at 298. How many electrons? 2 electrons lost, 2 electrons gained. Paradies is 96485. Natural log Q. Well, what is Q? So looking at this reaction, the only thing that is not going to cancel itself out is sulfuric acid. Sulfuric acid has, let's see, looking at sulfate. You have essentially sulfate and 2 equivalences. So I'm going to leave it all together, H2SO4 as H2SO. 4 squared. Balance, this is 1. Now I'm saying the whole ionic activity of the whole thing together. So 1 as the products, it's products over reactants. We don't include pure liquids, don't include pure solids. So I'm going to, yeah, so 1 over 0.2089 squared is equal to 22.915. So natural log of 22.915 times 8.314 times 298 divided by 2 divided by 96485. So it's subtracting 0.040. So what the cell potential of this guy under these conditions are 2.01 instead of 2.001 instead of 2.041. Not a huge change, but once again, this is pChem. We're trying to measure how does these things change from a real situation. So looking at this, if lead goes to lead 2 plus 2 electrons, and that is that cell potential, and lead 2 plus and plus water goes to lead oxide at 4 hydrogens, at 2 electrons, what would the Gibbs energy and cell potential be for this reaction? Of so lead going to, so essentially saying this goes products, this cancels out. So look at that cell potential. Cell potential is like, okay. Oh, so if we add them together, so if you add them together, you can't just say this is not what you can do. You can't just go. We cannot just go, well, the cell potential should be 0.1262 plus negative 1.455. We cannot just add those together. What we have to do is you have to find the delta G of each of those. So the first guy, 2 electrons times Faraday's. I'm going to leave it as F times 0.1262 equals 2 times Faraday's, 5 times R. So I'm going to turn this into kilojoules, negative 24.352, because Gibbs is a state function. E is not. So the second one, negative 1.455. That's going to be equal to positive 280.771. Now we can add these together. So we add these together. You get the net Gibbs is negative 256.418. And now we turn this back into the cell potential. So we have to multiply that by 1,000. Divide by, now we have 4 electrons, negative 4. So it's a positive. -4 divided by Faraday's, and then 6.485. And we have the cell potential is dropped to 0.6644. 6644. So it's not just a simple add these together, but it results in a much different change than you would expect. Yes, we should expect it's a lot less. A lot. You should expect that, oh, it is a change. But you do not expect the effect of the change. So there's a way you could calculate that by adding them together, but you can't just add the e's together without taking into account the n's. But so continuing. Entropy of this electrochemical reactions. Shown that we can measure Gibbs as a function of delta G equals negative NFE. Can we determine the entropy of this? That, well, entropy is a change in Gibbs with respect to T. So, and the change in entropy is going to be over positive NF. Changing, how does the cell potential change with temperature at a constant pressure? Simply put, if there's a temperature dependence, the cell potential is known, entropy can be easily calculated. It is, however, less accurate than calculating entropy through any other means due to the limited accuracy of this partial differential. So, and we can determine K. Through the NERNST equation, we've learned that delta G non-standard equals delta G standard RT ln Q, and that E non-standard equals E standard minus RT over NF ln Q. By definition, Q at equilibrium, Q equals K, and at equilibrium, delta G non-standard is equal to 0. And so E non-standard must also be 0 at equilibrium. With that in mind, we can find out what is K with respect to E standard. So now this equilibrium constant for many electrochemical reactions is often very large or very small, so determining K from other methods such as calculating activity is unfeasible. So using this equation, K can be determined with great accuracy for a simple voltmeter and can prove invaluable tool in determining the solubility product. When we determine E standard, by definition, it is assumed that all concentrations are 1 molar and all pressures are at 1 bar because of our standard state definition. But unfortunately, activity coefficients will vary widely at that concentration. They're not going to equal 1. There's no way they could. According to the Debye-Huckel limiting law, activity coefficients approach 1 at low concentrations. So we can extrapolate what E standard should be using measured E values at various dilute solutions. Take, for example, the reduction of silver ions paired with a standard hydrogen electrode. So silver plus goes to silver solid. Look at that. Looking at it from the perspective that we've defined that standard hydrogen electrode to be 0 volts, we only need to calculate the activity of silver. So since the activity, the mean ionic activity is equal to the mean ionic molarity times the mean ionic activity coefficient, you need to think about the anion as well. Things work out simply if you just assume silver is paired with a monoanionic species nitrate. So the mean ionic activity cation times activity anion raised to the power of coefficients, the sum of the coefficients. So if this is 1 and this is 1, it'd just be the square root of these two activities, which the activities, if the activities are equal for both those, then the activity of silver is just the mean ionic activity. So if this is x and this is x, x square root of x squared is x. So we can say those are the same. With that in mind, the same can be said thus then. The molarity, the mean ionic molarity is just the molarity of silver, and the mean ionic activity is just the activity of the silver. So from this, we can say replace K, or Q, with the activity of silver, which is then, and we're going to flip the sign, so make that negative positive, so it's instead of 1 over A, it's A. And then replace that, well, that's the molarity, and RT ln of the activity. So the Debye-Huckel limiting law says that low concentrations, that natural log activity is going to be equal to this whole mess of equation, which we calculated, or that's equal to the 1.7173 times the cation times anion square root of the I, and I would be the molality, essentially. Now, from there, taking that into account, so the natural log of log is E, take that in, take that, carry that through, we have essentially this, that cell potential is equal to cell potential standard RTF ln the molality, minus RTF times constant times the charge times molality, square root of molality. So evaluating for all known constants and keeping temperature constant at 298, we have essentially E non-standard equals E standard plus constant blah 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 ln molality minus constant over molality, the square root of molality. And so we can actually start to extrapolate. As we change these molalities and measure E, you can actually draw a line to where E standard would be, where E standard is the y-intercept. So we can plug these back in and extrapolate. So knowing that this is our E standard, is our E non-standard is our y, and our molality is our x, we can find what E standard should be. So that's something that could be done. Now we're going to finish off by just looking at some cell nomenclature and other stuff. So it's useful to have an abbreviated notation for electrochemical cell. Includes all species involved in the reaction and has a phase boundaries within the cell notation as a vertical line. Two half cells are written with oxidations, half cell on the left, reduction on the right. So anode on left, cathode on right. Electrodes appear on the ends, both sides in the notation. Now there can be additional contributions to the cell potential due to diffusion rates that are determined by ion. Yeah, so in a real cell, small ions will diffuse further and thus react faster with a liquid-liquid junction than a larger ions. At a steady state, a dipole layer will build up across the junction. Rates of ion transfer through this dipole layer is equal. So the kinetic effect will give rise to a small junction potential between two liquids of different composition and concentration. But so how do we get rid of that? We get rid of that by a salt bridge. And the interface for which is junction potential is eliminated using the two vertical lines. So just looking at this, zinc sulfate, the two vertical lines, copper sulfate, copper, silver chloride, and chloride ions, and thus iron 2 plus goes to platinum. What we see their solution, just how we deal with this. There's a line separating the gas from the aqueous. Double line shows so chloride and mercury chloride and mercury all in there, all with a platinum electrode. So this is actually the standard hydrogen electrode, and this is actually called the saturated calomel electrode, another well-known and well-studied electrode that's used as a standard. But we're just looking at what reaction's going to. We have this reaction, so total reaction is this. Silver solid plus chloride goes to silver chloride. Iron 3 plus goes iron 2 plus. Net reaction is that. Mercury, hydrogen goes to H plus. Mercury chloride goes to mercury and chloride. And so the last little thing is the electrochemical series. Because E standard over is equal to delta G standard over negative NF. Because Gibbs energy and cell potentials of all common electrical chemical cells are known, we can rank them in order of the spontaneity. These electrical chemical series are placed in a table listing the strongest oxidizing agents, easiest to be reduced on top, the weakest on the bottom. By consulting this list, we can easily determine whether a reaction will occur. The element that's highest on the table should be reduced. The lower element will always be oxidized. But the main reason we care about all this junk is because of batteries and fuel cells. Batteries contain all the reactants needed already, while fuel cells can get the reactants from the surroundings. If we compare the work of a battery to a heat engine, this is something very interesting. The electrical work is equal to negative delta G, which is equal to negative H times 1 minus T delta S over delta H, while the work thermal is equal to Q hot times the efficiency, whereas delta H, T hot minus T cold over T hot. Well, if you compare this, simple comparison, we'll see we can get a lot more work done simply through electrical work, in addition to the aspect of being a reusable battery. So batteries do not have the only problem, essentially, electrical work has 100% efficiency, which means if you can use a battery, you're not losing any energy. You can get the same amount of energy in as you got out without losing any to the environment. The only problem is that batteries don't have the same energy density, so you need a lot bigger batteries to be able to store the same amount as, say, a tank of gasoline. So a lot more energy per ounce of gas, but you lose a lot of that energy. So you kind of got that trade-off. So that's what we're trying to currently work on. So that's where we're stopping. This is not too impressive of a chapter. It is a chapter just built to try to help us understand some of the difficult concepts, or the easier concepts, and make them more physically chemical difficult in terms of how we deal with them. But, okay, that's the end of where I'm going. So please like, please subscribe. Have a good day.